Now the incident power, reflected and absorbed power in the transmission line. So here we have the transmission line, and let ZL is connected at Z equals to 0. So voltage across this will be VL, and this is the IL. So we will find out what is the incident power, reflected power, and the absorbed power here. So the incident voltage and current is given by this expression. You have the incident voltage is V naught plus e to the power minus j beta naught at this location. We want to find out what is the power at the incident wave at this point, what is the power which is reflected back at this location, and what is the power absorbed by this load. So we will talking about in this area. So at z equals to 0, so the forward traveling wave have the amplitude, this one V naught plus, and Vs Is. So this is the Is. Current is given by V naught plus as well. So the incident time average power is given by. So we will use a pointing vector, but now this will be written in terms of the voltage current. Earlier we have derived the last unit as this is the electric field and the magnetic field. Now you can easily obtain the power when you're talking about the voltage current. So this is given by this voltage, and this is the current, and you have this a complex. So here, so this will be the incident time average power, that is a pointing vector for the time average pointing vector. It will give you the power density. So when you take the real, this is at V as Z equals to 0 is V naught plus, and it will be V naught plus over Z naught. And when you write this the real power, the real part of this one, so you will get this PC and the half V naught plus whole square by Z naught. So generally we will consider the lossless line. So Z naught will be real for the lossless line here. Similarly, you can find this reflected power. So same location, but now we will find the power associated with the waves moving in the backward direction. So it will be given by Vs minus Z equals to 0. So you will see that you will get the expression here. This is how you will get this one half. Now already know that V naught negative is equals to magnitude is same as gamma L times you have the V naught positive. So when you take a magnitude using this expression, you can find that this will be the half gamma naught and gamma L are same thing here because load is connected. So gamma naught whole square is here. So what you can see, you can take it out here. It will be just the gamma naught square into P incident. So once you know the incident power and you know the reflection coefficient, just you can find the reflected power by just multiplying the square of this one. So this is a relation between the reflected power and the incident power. So this reflection coefficient will give you the relation between the incident power and the reflected power. Now what is the power absorbed by the load? The power absorbed by the load will be just you have this VL and IL, VL into IL, this is you will use. Now what is VL? VL is the total voltage at Z equals to 0, and IL is the total current at Z equals to 0, which is going into the load. So Vs will be sum of the incident voltage and the reflected voltage. Similarly, current will be sum of these two components. So when you simplify these expressions, so you will see that this absorbed power by the load will comes out to be this expression. This is the main expression. The power absorbed by the load will be V naught plus whole square by 2 Z naught 1 minus gamma naught whole square. So when you further split, this will comes out to be the absorbed power will be the incident power minus the reflected power. Whatever the power is reflected back, that has to be subtracted from this incident power. So this is a conservation of energy, that power cannot be created or destroyed. So it will be distributed. So whatever incident power is there, it will be distributed into two parts. One part will be absorbed by the load, and another part will be reflected by this load. So we have the total power will be the sum of the load power and the reflected power. Okay, so here this is a relation which is important. So once you know the incident power and using the reflection coefficient, you can find the absorbed power and the reflected power. So here you have the reflected power. So similarly, the absorbed power will be given by this expression. So you using this one, you can find the this one. So you can minus this P absorbed, just the P incident minus the P reference, and this is a P incident, and this is the part for the P. So you can find this one expression, total power. So for short circuit line, what do we have? Gamma naught equals to -1. So it means the whole power will be reflected back. No power will be absorbed because reflection coefficient is -1. The magnitude is 1. So P reference reflected power equals to P incident and no power will be absorbed. Similar for the open circuit line, when the circuit line is open, the reflection coefficient is +1. In this case also, the total power is reflected back and no power will be absorbed. And for the special case, when the this load is matched to the Z naught, as the ZL is matched to the transmission line, that is Z naught ZL equals to Z naught. In that case, the reflection coefficient is 0 and no power will be reflected back and the whole power is absorbed by the this load. So this is how you can compute the power between the incident wave, reflected wave, and the absorbed by the power absorbed by the load. Okay. So now in the next lecture we will talk about the input impedance.